KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we are going to discuss the next continuation example problem, that is example 10.8. After that, we are going to discuss the next important theory topic, viscosity. Okay, right. See here. First, see the example. That is what 10.8. See here, ma. A fully loaded Boeing aircraft. I think you might have seen this Boeing aircraft, right, which carries huge luggage, right? Okay, anyhow, if you take either luggage or human as in terms of mass, right, which carries heavy mass, right? See here, a fully loaded Boeing aircraft has a mass of 3.3 into 10 to the power of 5 kg. Its total wing area is 500 square meter. Its total wing area is 500 square meter, full stop. It is in level flight, okay. It is in level flight with a speed of 960 km. Right. It is level flight with a speed of 960 kilometers per hour. 960 kilometers per hour, right? This is the speed of the flight, ma. Now, there are two things we have to do. We have to estimate. First, A. Estimate the pressure difference between the lower and upper surfaces of the wings. B. Estimate the fractional increase. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. I'll repeat once again. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. Right. Here itself they have given density of air as 1.2 kilogram per meter cube. Rho is equal to 1.2 kilogram per meter cube. I will repeat once again. See the problem clearly. A fully loaded Boeing aircraft has a mass of 3.3 into 10 to the power of 5 kg. Right. It is what the mass of the Boeing aircraft. Its total wing area also given 500 square meter. And it is level flight with a speed of 960 kilometers per hour. That is the speed of the flight. Asking to estimate the pressure difference between the lower and upper surfaces of the wings. Next, asking to estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface of air. Right. They have given the density of air also. Lower surface. Right, asking to estimate the fractional increase in the speed of the air on the upper surface of the wing related to the lower surface. They have given the density of air is 1.2 kilogram per meter cube. Right. See, in this problem, they have given mass of the Boeing aircraft and wing area and speed of the flight and density of air. Four things they have given. Asking to estimate pressure difference between the lower and upper surfaces of the wings and estimate that is what to calculate fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface, right? That's what they have given. Now, see the answer. Okay, see here. First A. See, there are two things, no, A and B. First, we are going to complete A, then we will go for B. A. The weight of the Boeing aircraft. The weight of the Boeing aircraft is balanced by. The weight of the Boeing aircraft is balanced by the upward force due to the pressure difference. It is what the statement you can write conceptually. The weight of the Boeing aircraft is balanced by the upward force due to the pressure difference. So that what can we write? See, the mass is multiplied with 9.8 to get the weight. So 3.3 into 10 to the power of 5 kg into 9.8. This side, that is what left hand side, delta P into A. But now we need to find delta P now. Area of the wing already given, that is what 500 square meter, right? So it is already available in SI. So now here delta P is equal to 3.3 into 10 to the power of 5 kg into 9.8 meter per second square divided by 500. So if we complete this mathematical division here, and after completion of that, if we have divided with 500, so which will give us 6.5 into 10 to the power of 3. 6.5 into 10 to the power of 3 Newton per meter square. Delta P is equal to 6.5 into 10 to the power of 3 Newton per meter square. Next, B. It is A, it is B. In case of B, he is asking to estimate. In case of B, he is asking to estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. Okay, right. See this. First, we ignore the small height. We ignore the small height difference between the top and bottom sides. See, what is the height of the aeroplane? You can imagine. So we are neglecting that height. So we ignore the small height difference between the top and bottom sides. Now, the pressure difference between them is, then delta P is equal to rho by 2 into V2 square minus V1 square. Rho by 2 into V2 square minus V1 square. V2 is the speed of the air on the upper surface, and V2 is the speed of the air under the bottom surface. Now, V2 minus V1 is equal to 2 into delta P by 2 into delta P divided by rho into V2 plus V1. V2 plus V1. That is what here we are taking the average speed. Average speed means what? V average is equal to V2 plus V1 by 2. Average speed means V average is equal to V2 plus V1 by 2. That is equal to 960 kilometers per hour he has already given. So that is equal to, if you convert this kilometers per hour into meters per second, that is 267 meter per second. V average is equal to 267 meter per second. We have V2 minus V1 divided by V average is equal, because it is V2 minus V1 now. So 2 into delta P divided by rho into V2 plus V1 divided by V2 plus V1 divided by 2. Then finally we are getting delta P divided by rho average square. Delta P divided by rho average square, which is approximately equal to 0.08, which we are getting approximately 0.08. So 0.08 means you can write 8 by 100 now. 8 by 100. So when we are going to say this result in terms of percentage, the speed above the wing needs to be only 8% higher than that below. The speed above the wing needs to be only 8% higher than that below. That is what we can say. Because based on this expression, we can say speed above the wing needs to be only 8% higher than that below. So in this problem, one of the important problem regarding the applications to daily life, because what is aircraft, what is Boeing aircraft, what is aeroplane, how the aeroplane is, what are the wings, where the aeroplane is moving, right? That is what the motion of the aeroplane is among the fluid. That is also one of the important fluid in our daily life. That is what air. So this is what we experienced. So related to that, this is the problem. In this problem, as simple as such, he is asking to estimate the pressure difference between the lower and upper surfaces of the wings. That is what we got, 6.5 into 10 to the power of 3 Newton per meter square. After that, he is asking to estimate the fractional increase in the speed of the air. Fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. That is what we calculated. It is 8% higher than that below. The speed above the wing needs to be only 8% higher than that below by using these three steps. So the first one is regarding the pressure difference, delta P is equal rho by 2 into V2 square minus V1 square. And the second step here, V2 minus V1 is equal to 2 into delta P divided by rho into V2 plus V1. And then here V average is equal to V2 plus V1 by 2, that is equal to 960 kilometers per hour, that is equal to 267 meters per second, right? So finally here V2 minus V1 by V average, if you take the ratio of V2 minus V1 to the V average, we are getting approximately 0.08. Based on that, you can conclude the speed above the wing needs to be only 8% higher than that below. Next continuation, a theoretical topic, most important theoretical topic, viscosity. See, for example, there are two bottles. In one bottle, water molecules are present. In another bottle, honey is present, right? Honey. If you try to pour down these two things, you may observe certain difference. What is the difference? While pouring water from a water bottle, it is easy and you can easily pour. But while pouring honey to down, what will happen? It takes certain time, right? It comes slowly from the bottle. See, where is the difference? The difference is viscosity, viscous force, the internal friction among the fluid layers. I am asking you, just imagine the fluid which is present in the bottle like this, like different layers. See, when water or honey, whatever it may be, the fluid which tries to comes out, every layer, either top layer or bottom layer or second layer, third layer, fourth layer, whatever it may be, every layer tries to stop the motion of the second layer, next layer. Similarly, that next layer tries to stop the motion of the another layer. But anyhow, when you are applying more amount of force, more force, higher in magnitude, so because of not able to overcome this applied force, the fluid will come out. But the internal friction, so viscosity is nothing but the internal friction among the fluid levels or fluid layers. That's what here you can see. Resistance to fluid motion. Resistance to fluid motion is like an internal friction analogous to friction. That is what we discussed in the chapter of laws of motion now. That is, so how we experience the friction when we are walking on surface of earth. Similarly, fluid levels, that is what fluid also experience some resistance to come out of the or to move from one point to another point. So based on this example, he is concluding resistance to fluid motion is like an internal friction analogous to friction. Right. Next, when a solid moves on a surface, this is what friction we experience when a solid moves on a surface. But it is the fluid, resistance to fluid motion means it is like viscosity, that we are calling it as viscosity. So that here he is saying it is called viscosity. So these three lines gives complete information about the viscosity. That's what you can say. Resistance to fluid motion is like an internal friction analogous to friction when a solid moves on a surface. Okay, right. The force exists when there is relative motion between layers of the liquid. Viscous force is the force exists when there is a relative motion between layers of a liquid or fluid. Suppose if you consider a fluid like oil enclosed between two glass plates, that you can see like this. See, while taking the blood test, right? While getting the blood test, you are using some glass plates. You just take the two glass plates and you just dip the two glass plates in the oil, okay? in the oil, right? So after completion of that dipping into the oil, you just take it out and you just see how the oil distributing between the two plates. That is the situation here. When you consider a fluid like oil enclosed between two glass plates, the bottom plate is fixed while the top plate is moved with a constant velocity relative to the fixed plate. Okay, that is what you can see in this picture, right? This is what. And I can say one more point here. If you replace that oil with honey, a greater force is required to move the plate with the same velocity. That's why you can say honey is more viscous than oil. Honey is more viscous than oil. Right now, the fluid in contact with the surface has the same velocity as that of the surfaces. So this is the plate. So what this plate velocity means, this fluid. So whatever the fluid velocity is present here for this particular fluid layer, the same as like glass plate. The layer of the fluid in contact with the top surface moves with a velocity v, and the layer of the liquid in contact with the fixed surface is stationary. This is the stationary, which is the stationary. This is what moving with some speed. That speed is same as the speed of this top layer. You can imagine. The velocities of layers increases uniformly from bottom to the top. Right? For any layer of a liquid, its upper layer pulls it forward while lower layer pulls it backwards. You can see this picture is giving complete information about viscosity and the information what I am discussing to you. This results in a force between the layers. Right? This type of flow is known as laminar flow. Laminar, laminar flow. The layers of liquid slide over one another as the pages of a book do when it is placed on a flat table and a horizontal force is applied on the top cover. This is what you have to experience personally. You just keep the book on the table and you just take the top paper and you just try to pull. What's happening? In a similar manner, the fluid behaves when it is coming out from a bottle. When a fluid is flowing in a pipe or a tube, like the same situation, you can experience how the book behaves by pulling the top page or the top paper of the book. The velocity of the liquid layer along the axis of the tube is maximum and decreases gradually as we move towards the walls, where it becomes zero. The velocity on a cylindrical surface in a tube is constant. Here you can see. See, here it is top, decreasing, and finally decreasing. Right. Now, a portion of liquid which at some instant has the shape A, B, C, D, for example, it is what A, B, C, D, right? A, this is what A, it is B, it is C, and okay, see here, so we are going to derive an expression for viscous force. First we are going to derive for coefficient of viscosity, then we will discuss about viscous force. So regarding this topic, on account of this motion, a portion of liquid which is at some instant has the shape A, B, C, D. A, B, C, D. You can see in the figure. Now, take the shape of AEFD. AEFD after a short interval of time. So that this is the displacement. See here, delta x is equal to V into delta t is the displacement. Delta x is equal to V into delta t is the displacement. During this time interval, the liquid has undergone a shear strain of delta x by L. It is L, it is delta x. So within this time interval, for example delta t, liquid goes to get the shear strain. Liquid is undergoing a shear strain, that is what delta x by L. In our last chapter, mechanical properties of solids, we discussed what is the shear stress and what is the shear strain. Now, unlike a solid here, see whatever the shear strain the liquid is going to experience, which increases with time continuously. Now, unlike a solid, the stress is found experimentally to depend on rate of change of strain, rate of change of strain or strain rate, that is what delta x by L into delta t, delta x by L into delta t, or V by L, or V by L instead of strain itself. Now we are going to discuss the important quantity which helps us to calculate the viscous force, that is coefficient of viscosity, coefficient of viscosity. So the coefficient of viscosity for a fluid is defined as the ratio of shearing stress to the strain rate. Eta is equal to, eta is the symbol we are using to represent coefficient of viscosity. Eta is equal to F by A divided by V by L, that is equal to F into L by A into V. The SI unit of coefficient of viscosity is Poissonic. So you can use PL. Okay, you can use PL short form. Its other units, it is L, it is not I, it is L, PL. Its other units are Newton second per meter square, otherwise Pascal second. Next, what is the dimensional formula? M power 1, L power minus 1, T power minus 1. M power 1, L power minus 1, T power minus 1. Generally, if you take thin liquids like water, alcohol, etc., are less viscous than thick liquids like coal tar, blood, glycerin, etc. Right? It's a general experience, no? You can see in our biology lab or in our physics lab, right? In our daily life also. See, when we are going to get blood test, you can see what is the movement of the blood molecules from one place to another place. Okay, platelets are present, right? That's you can see. Now, the coefficient of viscosity for some common fluids, that's we are going to see in this same chapter. They have given one table. That table I will put in front of you in the next coming class. We point out the two facts about the blood and water. What are those 2 points? What are the two facts? See, for example, if you see the table, right, I will tell you the value. Blood is thicker than water. Blood is thicker than water because for the blood the viscosity is 2.7. For the water, which is 1.0 at 20 degrees centigrade. 20 degrees centigrade means right? 20 degrees centigrade means like at ordinary temperature or room temperature. So you can also see the relative viscosity, that is viscosity of the substance, ratio of viscosity of a substance or fluid to the viscosity of water. Viscosity of water, that is remains constant between 0 degree centigrade to and 30 degree centigrade, 37 degree centigrade for blood. And one more important point at last you can say, that is the relation between viscosity and temperature. That is, the viscosity of liquids decreases with the temperature, while in case of gas it will be increases. That's what you can say. In this class we discussed one example problem, that is example 10.8. After completion of that, we discussed the most important theoretical topic, viscosity. Okay, right. In our next class, we are going to discuss next continuation example problem, that is example 10.9. After completion of that, we will discuss very important for a board and neat point of view, that is Stokes' law, which helps us to determine the viscous force. Okay, thank you.